Look up at the night sky, past the familiar glow of the moon, past the steady light of our neighbor Mars, and you will find it, a brilliant, unblinking beacon, a world so vast that all the other planets in our solar system could fit inside it with room to spare. This is Jupiter, not merely a planet but a cosmic sovereign, a swirling tapestry of violent beauty and profound secrets that has captivated humanity since the first time we gazed upwards. For centuries, we could only wonder what lay within those hypnotic cloud bands, but now, thanks to eyes like the Juno spacecraft, we are closer than ever to the truth. And the truth is more mysterious, more baffling, and more magnificent than we ever dreamed. So we have to ask, what incredible secrets are still hidden beneath those endless, churning storms? This video is an expedition into the heart of that mystery. We are going to journey together through 25 of the most perplexing, head-scratching, and outright astonishing enigmas that Jupiter has to offer. This is not just a tour of a giant ball of gas. It is a deep dive into a world of immense power, where auroras rage with energies that dwarf our own, where a storm larger than our entire planet has raged for hundreds of years, and where the very interior of the planet may hold substances and states of matter that defy our understanding of physics. We will grapple with questions that scientists are still struggling to answer. Does Jupiter have a solid core, or is it something far stranger? What is the true nature of the Great Red Spot, and is it finally dying? How does a planet with no solid surface generate a magnetic field so powerful it creates its own miniature version of a solar system? But our journey won't stop at the planet itself. We will venture out to its extraordinary family of moons, worlds that are themselves realms of profound mystery. We will explore the volcanic fury of Io, the hidden global ocean of Europa that may just harbor life, and the bewildering grooved terrain of Ganymede. Each of these moons is a story unto itself, a chapter in the epic saga of the Jovian system. So get ready to have your curiosity ignited and your sense of wonder expanded. The greatest king of our solar system is ready to reveal its secrets, and what we are about to discover will change the way you see our cosmic neighborhood forever. And so we begin our journey into the unknown with the most iconic feature in the entire solar system, a sight so familiar yet so alien, the Great Red Spot. If you were to somehow fly a spacecraft directly towards this colossal maelstrom, the scale would be almost impossible to comprehend. This is not a storm, it is a storm system, an anticyclone so vast that our entire planet Earth could be swallowed whole within its swirling, brick-red borders with room to spare. We have documented its churning fury for at least 190 years, since astronomers first trained their telescopes on it in the 19th century, and some speculate, based on earlier sketches, that it may have been raging for over 350 years. That single fact alone shatters everything we know about planetary weather. On Earth, the most powerful hurricanes, fueled by warm ocean waters, exhaust themselves in a matter of days once they hit land or cooler seas. Yet here, on a world with no solid surface to break it apart, a hurricane of almost unimaginable power has been spinning for centuries. The central, baffling question is simple: what is the engine that drives this perpetual tempest? The answer appears to lie deep within Jupiter itself. Unlike Earth, which gets most of its weather energy from the sun, Jupiter is a powerhouse generating its own immense internal heat, left over from its formation billions of years ago. This planet is still slowly contracting under its own gravity, and that process releases staggering amounts of thermal energy upward, like a cosmic engine stoking the fires of its atmosphere from below. The Great Red Spot acts like a giant atmospheric wheel, tapping into these vertical currents and the powerful jet streams that race around the planet to maintain its ferocious spin. It's also a cosmic bully, absorbing smaller storms that wander too close, cannibalizing their energy and momentum to sustain its own longevity. Think of it not as a solitary storm, but as the dominant feature in a chaotic, planet-wide weather system, a self-sustaining vortex that has found a terrifyingly stable equilibrium. But this seemingly eternal giant is showing signs of change, adding a thrilling layer of modern intrigue to its ancient mystery. For decades, astronomers have been carefully measuring the Great Red Spot, and the data reveals a clear and startling trend: it is shrinking. Its width has decreased significantly, and some observations suggest it is becoming more circular than its traditional oval shape. This has sparked a vigorous debate among planetary scientists. Are we witnessing the slow, inevitable death of a solar system legend? Or is this simply a natural phase in a cycle we do not yet understand? Some theories suggest that the storm is being disrupted by interactions with other jet streams, or that it is somehow losing the energy source that has sustained it for so long. The fate of the Great Red Spot is now one of the most urgent questions in planetary science, a race against time to understand the inner workings of this magnificent beast before it potentially vanishes from the Jovian sky, leaving behind only a legend and a profound mystery about the life cycle of storms on a giant world. Yet for all its grandeur, the Great Red Spot is merely a symptom of a far deeper, more fundamental power raging within Jupiter. To understand the true nature of this giant, we must turn our attention from what happens on its surface to what is happening deep inside it, and that brings us directly to our second great mystery, the furnace within. Imagine holding your hands out towards a campfire. You feel the warmth radiating from the flames. Now, imagine that same campfire generating its own intense heat, even when no one is adding wood. This is the paradox of Jupiter. Measurements from spacecraft have confirmed a startling fact. The planet emits more than twice the amount of heat that it receives from the sun. It is a cosmic powerhouse glowing with its own internal energy, and the source of that heat has been a puzzle for decades. The leading explanation for this immense thermal output is a process known as Kelvin-Helmholtz contraction. The idea is elegantly simple, yet its implications are profound. Jupiter has an almost unimaginable mass, and its own immense gravity is constantly pulling everything inward, trying to compress the planet into a smaller, denser sphere. This incredibly slow gravitational squeezing, a contraction over billions of years, converts gravitational potential energy into thermal energy, into heat. Think of it as a planet-sized version of pumping air into a bicycle tire. The pump gets warm because you are compressing the air inside. Jupiter has been doing this on a planetary scale since its formation, and that residual heat from its violent birth, combined with this ongoing contraction, is thought to be the primary engine warming the planet from the inside out. But is that the whole story? Many scientists suspect that Kelvin-Helmholtz contraction alone might not be sufficient to account for the sheer volume of heat we observe. This has opened the door to some fascinating alternative theories that venture into even stranger physical realms. One compelling idea involves a phenomenon that sounds like it's straight out of science fiction: helium rain. Deep within Jupiter's atmosphere, under pressures and temperatures that defy comprehension, hydrogen is compressed into a metallic, fluid state. Under these extreme conditions, it's theorized that helium may not mix perfectly with this metallic hydrogen. Instead, it could condense into droplets and literally rain down through the liquid metallic interior. As these countless droplets fall deeper into the gravity well, they would release additional gravitational energy, which is converted into more heat, essentially creating a continuous internal heater. This leads to even more exotic questions about the very heart of the planet. What is the nature of Jupiter's core? Is there a solid rocky center, or has the intense pressure and heat over billions of years created something entirely different, a diffuse, diluted core where heavy elements are mixed throughout the interior? The processes happening at this central point could also be contributing significant thermal energy through radioactive decay or other. yet unknown mechanisms related to the behavior of matter under such extreme duress. Unraveling the precise recipe of Jupiter's internal furnace is not just an academic exercise. It is the key to understanding everything about the planet, from the ferocity of its storms to the unbelievable strength of its magnetic field. This internal heat is the breath of life for the Jovian system, and we are only just beginning to understand the complex physics that keeps this giant world warm. But that internal furnace, as powerful as it is, only hints at the even greater mystery that lies beneath it. To truly grasp the forces at work on Jupiter, we must journey beyond the storms and the heat and venture towards the very center of the planet itself. This brings us to our third and perhaps most profound enigma, the nature of Jupiter's core. What actually lies at the heart of this giant? For decades, the prevailing theory was a relatively straightforward one. Scientists imagined that during the solar system's formation, a solid, rocky core, perhaps 10 to 20 times the mass of Earth, formed first through the accumulation of dust and ice. This massive seed then possessed enough gravitational pull to attract the vast envelope of hydrogen and helium gas that makes up the bulk of the planet we see today. In this model, Jupiter's core was a distinct, compact, and incredibly dense sphere of rock and metal, a fossil from the dawn of our planetary system. This neat and tidy picture, however, has been completely upended by the revolutionary data sent back by the Juno spacecraft. By precisely measuring Jupiter's gravitational field with exquisite accuracy, Juno has revealed that the core is not the dense, compact ball we once thought. Instead, the data points to something far stranger, something that challenges the very foundations of planetary science. The core appears to be fuzzy or diluted. This means that the heavy elements, the rocks and metals that supposedly formed the initial seed, are not concentrated in a neat central sphere. They seem to be partially dissolved and spread out across a significant portion of the planet's interior, mixing with the inner layers of metallic hydrogen in a vast, diffuse region that may extend up to half of Jupiter's radius. It's as if the solid core we imagined has been slowly stirred into the liquid metallic hydrogen soup surrounding it over billions of years. This discovery has monumental implications for how we understand the formation of not just Jupiter, but all gas giants. The traditional core accretion model, while still a crucial part of the story, now seems incomplete. A fuzzy core suggests a much more violent and chaotic formation process. One leading theory is that after its initial formation, a young Jupiter was struck by a colossal impact with another planetary-sized object. This catastrophic collision could have shattered and scattered the original dense core, mixing its material throughout the inner layers. It's a dramatic vision of the early solar system as a cosmic shooting gallery, where the fate of the largest planet was sealed by a single, unimaginably powerful event. Alternatively, the dilution might be a more gradual process, driven by intense heat and convection currents within the metallic hydrogen layer, slowly eroding and dissolving the core over eons. This blurred boundary at Jupiter's heart also forces us to reconsider the very definition of a planetary core. Is it a place where one substance ends and another begins? Or is it a gradual transition zone where materials blend together under unimaginable pressure? The answer to this question doesn't just rewrite the history of our solar system. It has profound implications for the thousands of giant exoplanets we have discovered orbiting other stars. If Jupiter, our archetypal gas giant, doesn't have a classic solid core, then we must rethink the possible internal structures of all such worlds. The mystery of Jupiter's core is a gateway to understanding the diverse and often violent ways that planetary systems are built, revealing that even the mightiest of planets can have a surprisingly complex and ill-defined heart. If the churning atmosphere and the deep internal heat of Jupiter represent its raw physical power, then its magnetic field is the ultimate expression of that power on a cosmic scale. We are venturing now into the fourth great mystery, a phenomenon so immense that its influence extends millions of miles into space, creating a protective bubble or magnetosphere that is the largest single structure in our entire solar system. If you could see Jupiter's magnetic field with your own eyes, it would appear larger than the full moon in our sky, a colossal, invisible force field that shields the planet from the supersonic wind streaming from the sun. The numbers alone are staggering. Jupiter's magnetic field is about 20,000 times stronger than the magnetic field of Earth. This isn't just a slight difference, it is a difference of cosmic proportions, a testament to the titanic forces operating deep within the giant world. So, how does Jupiter generate such an unimaginably powerful field? The answer lies in the bizarre behavior of matter under extreme conditions, a process known as a dynamo. Here on Earth, our magnetic field is created by the churning of molten iron and nickel in the outer core. Jupiter, however, is not a rocky planet with a molten metal core. Its magnetic engine is something far more exotic. Deep within the planet, where pressures exceed millions of Earth atmospheres, hydrogen, the simplest and most abundant element in the universe, undergoes a breathtaking transformation. It is squeezed into a state that defies normal physics, becoming a liquid metal. This metallic hydrogen is an incredible substance, a fluid that can conduct electricity as well as any metal on Earth. As Jupiter rotates at a dizzying speed, completing a day in just under 10 hours, this vast, deep ocean of electrically conductive liquid is set into motion. This churning, convecting fluid acts like a planet-sized electrical generator, and the movement of this conductor through the planet's own magnetic fields generates immense electrical currents, which in turn amplify the magnetic field in a self-sustaining feedback loop. It is a perfect, powerful dynamo, but one operating on a scale we can barely comprehend. For years, scientists assumed this dynamo would operate in a relatively orderly fashion, perhaps creating a magnetic field that was somewhat lopsided but generally predictable. That assumption was completely shattered when NASA's Juno spacecraft began its precise mapping of the field. What Juno found was not a neat, structured field, but something far more chaotic and mysterious. The magnetic field is remarkably lumpy and irregular, and it possesses a profound and puzzling asymmetry. It is significantly stronger and more complex in the northern hemisphere than it is in the south. This was completely unexpected and presents a direct challenge to our established models of how planetary magnetic fields are supposed to work. A lopsided field suggests that the dynamo engine itself is lopsided, that the flow of metallic hydrogen is not uniform around the planet's core. This irregularity is a critical clue, a message from the deep interior about the hidden dynamics of Jupiter. One compelling theory to explain the lumpiness is that the dynamo action is not occurring in one single, deep shell of metallic hydrogen. Instead, it might be happening in multiple, separate layers at different depths. There could be complex weather patterns within the metallic hydrogen itself, with jets and storms of this fluid metal creating pockets of intense magnetic activity. Much like storms in the outer atmosphere create localized zones of high and low pressure. The stark difference between the northern and southern hemispheres might indicate that the boundary of the dynamo region, the point where hydrogen transitions from a gas to a metal, is shallower in the north than in the south. This could be due to variations in temperature or pressure deep within the planet, creating a fundamentally different environment for the dynamo to operate in each hemisphere. Understanding this magnetic mystery is not just about solving a puzzle for its own sake. Jupiter's powerful magnetosphere has a direct and dramatic impact on its moons, bathing them in intense radiation and shaping their potential for habitability. The irregularities in the field also affect where and how dangerous radiation belts are formed, which is crucial information for planning future missions to explore the Jovian system. By deciphering the strange, lumpy signature of Jupiter's magnetic field, we are essentially learning to read the hidden currents and flows of its deep interior. gaining an unprecedented window into the behavior of matter under the most extreme conditions nature can produce. The true depth of this magnetic strangeness, however, was only revealed when Juno's instruments focused in on a feature that sounds like it belongs in a fantasy novel, but is very much a reality: the Great Blue Spot. Found near Jupiter's equator, this is not a swirling storm of clouds like the Great Red Spot, but an intense, localized knot in the planet's magnetic field. Imagine a powerful, concentrated magnet buried deep within the planet, its influence punching upward through the chaotic magnetic tapestry to create a bizarre and isolated anomaly. It is a feature utterly unique in our solar system, with no known counterpart on Earth or any other planet we have studied. The discovery of the Great Blue Spot forced scientists to completely rethink their models of Jupiter's interior. The leading explanation for this peculiar feature points to a dramatic phenomenon occurring in the abyss below, a hurricane of hydrogen, deep within the planet where hydrogen exists in its exotic, liquid metallic form. It is believed that a particularly powerful and narrow jet stream of this fluid metal is flowing. On Earth, we have jet streams of air high in the atmosphere. On Jupiter, they have jet streams of electrically conductive liquid metal deep in its interior. This flowing river of metallic hydrogen acts like a massive electrical current, and as it moves through the planet's pre-existing magnetic field, it generates a new, intensely localized magnetic field of its own, the Great Blue Spot we detect from above. It is essentially a planetary scale generator, a dynamo within a dynamo, creating a magnetic storm trapped within the depths of the planet. Why this magnetic hurricane exists specifically at the equator adds another layer of intrigue. The dynamics of a spinning fluid sphere, especially one as complex as Jupiter's interior, can create unique conditions at the equator that are not present at the poles or mid-latitudes. Here, the powerful Coriolis force, which influences rotating fluids, may act in a way that allows for the stabilization of such a concentrated jet. It's possible that this equatorial jet is a remnant from Jupiter's earliest days, a stable current that has been flowing for billions of years, or it could be a more recent feature born from the complex interaction between different layers of the interior. Its precise depth and what exactly anchors it in place are still active subjects of research, but its existence highlights that Jupiter's interior is not a homogeneous fluid ball, but a world of distinct structures and weather patterns even thousands of miles beneath the visible cloud tops. The presence of the Great Blue Spot is not just a curious oddity, it has a direct and measurable impact on the entire Jovian system. This concentrated magnetic patch significantly contributes to the overall lopsided and warped shape of Jupiter's magnetosphere. The planet's magnetic field is not a smooth, symmetric bubble extending into space. Instead, it is tugged and distorted by these intense internal anomalies, particularly the Great Blue Spot. This creates regions where the magnetic field is weaker or stronger, which in turn influences the behavior of the vast swarms of charged particles trapped within Jupiter's radiation belts. For any future spacecraft venturing close to Jupiter, especially near the equator, understanding the precise location and strength of the Great Blue Spot is critical for navigating the most hazardous zones of radiation. This deep-seated magnetic hurricane, invisible to our eyes, therefore shapes the very environment of space around the King of Planets, proving that the mysteries of Jupiter's interior reach out to touch everything that orbits it. Moving from the hidden dynamo of the magnetic field to the stunning visual spectacle of the planet itself, we arrive at one of the most recognizable features in the cosmos, Jupiter's stripes. That beautiful, hypnotic pattern of alternating light and dark bands is not just a static painting, it is a live broadcast of the most powerful weather system we have ever seen. These stripes are, in fact, the tops of colossal jet streams racing around the planet at speeds that can exceed 400 miles per hour. The lighter-colored bands are called zones, and they are regions of rising air. Think of them as planet-sized high-pressure systems where ammonia-rich gas is welling up from the warmer depths, cooling as it rises and forming bright, white clouds of ammonia ice crystals. They are the cloud-covered mountain ranges of Jupiter's atmosphere. In contrast, the darker bands, known as belts, are the opposite. Here, the air is sinking, diving back down into the planet's hot interior. As it descends, it clears away the high, bright ammonia clouds, allowing us to see deeper into the atmosphere where the air is warmer, drier, and populated by a completely different set of chemicals that give the belts their darker, reddish-brown hues. This simple upwelling and downwelling cycle, a planet-wide convection current, is the engine that drives the entire striped appearance. Yet, for all we understand about the dynamics, a central and vibrant mystery remains. What exactly is the chemical cocktail that creates the specific colors? The bright white of the zones is the easiest to explain. It is almost certainly the reflective power of ammonia ice. But the rich palette of tans, browns, oranges, and even subtle reds that color the belts is a far more complex puzzle. Sunlight plays a crucial role, acting as a cosmic artist's brush. High-energy ultraviolet radiation from the sun bombards the chemicals in Jupiter's atmosphere, breaking apart simple molecules like methane and ammonia and allowing the fragments to recombine into more complex compounds. This process, known as photochemistry, is likely creating a soup of exotic hydrocarbons and other complex molecules. The particular color we see depends heavily on the depth and composition of the atmosphere we are looking at. Those darker belts, being regions of sinking, clearer air, offer a window to a deeper, warmer layer where these mysterious compounds can form and become concentrated. Scientists have proposed a fascinating array of suspects for these color-giving compounds. One leading theory points to complex molecules containing phosphorus, sulfur, or carbon. It is possible that the breakdown of phosphine gas, a molecule made of phosphorus and hydrogen that is found in Jupiter's deeper atmosphere, could be creating red phosphorus or other phosphorus-based compounds that have a reddish hue. Another compelling idea involves a family of chemicals called tholins. Tholins are large, complex organic molecules that form when simple carbon-containing compounds like methane are irradiated. They are not a single specific substance, but a class of reddish-brown, tar-like compounds that are thought to be common on many worlds in the outer solar system. We see their coloration on places like Pluto and Saturn's moon Titan. It is highly probable that a similar process is occurring on Jupiter, with tholins forming in the belts and providing their characteristic coloring. The true mystery, however, is that no single compound we have been able to recreate in a laboratory perfectly matches the spectral signature, the unique chemical fingerprint of light that we observe from Jupiter's clouds. This suggests that the actual coloring agent might be a blend of several different compounds, or it could be a substance that only forms under the very specific and extreme conditions found deep within the Jovian atmosphere, a combination of intense pressure, high temperature, and specific levels of solar radiation that we cannot yet replicate. The beautiful stripes of Jupiter are therefore more than just a pretty face. They are a complex chemical factory and a stunning visual representation of the dynamic and poorly understood interactions between a planet's deep interior, its atmosphere, and the light from its star. Decoding their exact composition is like trying to identify every spice in a cosmic stew by only smelling it from millions of miles away. The beautiful, swirling stripes of Jupiter present a visual mystery of color, but if we could peer deeper past the cloud tops, we would encounter a question of profound importance to the very history of our solar system, the mystery of water. This is not about oceans on the surface, but about water vapor hidden within the atmosphere, and determining its abundance is one of the most crucial and frustrating puzzles scientists face. Water was a fundamental building block in the early solar system. The line beyond which water could condense into ice, called the frost line, essentially dictated the architecture of the planets. Inside this line, where it was warmer, rocky planets like Earth and Mars formed. Outside it, water ice was plentiful, allowing the cores of gas giants like Jupiter to rapidly accumulate vast amounts of material. So, by measuring how much water is in Jupiter's atmosphere today, we are essentially taking a core sample from the planet's birth, testing the very theories of how our planetary system came to be. For decades, our best chance to get a direct measurement came from a brave little spacecraft, the Galileo probe. In 1995, Galileo released an atmospheric probe that plunged into a seemingly typical region of Jupiter's clouds. As it descended, it radioed back data on the chemical composition it encountered. The results sent shockwaves through the planetary science community. The probe had entered what scientists later called a hotspot, a localized region of unusually dry and warm descending air. In this spot, the water abundance was startlingly low, almost desert-like compared to what was expected. If this measurement was representative of the entire planet, it would force a complete rewrite of solar system formation models. How could the king of the planets, which formed in the cold outer reaches where water ice was abundant, be so parched? It was as if we had drilled a single hole in the Sahara and concluded the entire Earth was a desert, completely missing the oceans. The truth, as we are now learning from the Juno mission, is that Jupiter is a world of stunning atmospheric variety, and the Galileo probe was just profoundly unlucky in its landing site. Juno, equipped with a sophisticated microwave radiometer, has a unique ability to peer dozens of miles beneath the visible cloud tops to sense water vapor at different depths and across vast stretches of the planet. Its data paints a completely different and far more complex picture. Juno suggests that near the equator, water may make up about 0.25% of the molecules in the atmosphere. While that might sound like a tiny amount on a planet of Jupiter's scale, it represents a staggering quantity of water. The real revelation, however, is that this water is not evenly mixed at all. Its distribution is wildly variable, with some regions appearing significantly wetter or drier than others. The Galileo probe didn't find a dry Jupiter, it simply stumbled into one of the planet's driest pockets. This uneven distribution is the heart of the modern mystery. Why is Jupiter's water so patchy? The answer likely lies in the planet's incredibly powerful and complex internal weather. Jupiter's atmosphere is not a well-stirred cocktail. It is a seething cauldron of convection and powerful downdrafts. Those dark belts where air is sinking act like atmospheric drains, pulling drier air from the upper atmosphere down to great depths. Conversely, the bright zones where air is rising carry warmer, moister air upward from the interior. The Galileo probe descended directly into one of these draining belts, a hotspot, which explains why it found such a dry environment. Juno's global observations confirm that the concentration of water is tightly linked to these colossal weather patterns. The water we can detect is not necessarily a perfect reflection of the planet's bulk abundance. It is what the planet's violent circulation chooses to reveal to us at a particular place and time. This leads to an even deeper question. Where did this water come from in the first place, and what does its distribution tell us about Jupiter's interior? One possibility is that the water we see is primarily external, delivered by the countless comets that have bombarded Jupiter over billions of years. However, many scientists believe a significant portion is native, trapped deep within the planet since its formation. If this internal reservoir exists, then the variable water abundance measured in the upper atmosphere becomes a tracer, a chemical clue that allows us to map the planet's hidden circulation. The moist air rising in the zones might be giving us a fleeting glimpse of this deeply buried water, suggesting that Jupiter's interior could be far richer in oxygen than we ever imagined. Unraveling this puzzle is more than an academic exercise. It is the key to determining whether our standard model of a water-rich Jupiter forming beyond the frost line is correct, or if the planet's history was far more complex and turbulent than we ever dreamed. But if the swirling colors of Jupiter's atmosphere represent a chemical mystery, the planet's poles present a spectacle of pure, raw energy that dwarfs anything else in our solar system. Here, at the very top and bottom of the world, the sky is set ablaze with permanent, planet-sized auroras. These are not the delicate, shimmering curtains of green and red we occasionally see on Earth. These are colossal, raging infernos of light, hundreds of times more energetic than our own. If you could stand on Jupiter's cloud tops beneath this display, the auroras would be brighter than the full moon, a continuous, blinding storm of radiation that would be instantly lethal to any life. They are the largest and most powerful auroras we know of, and their very existence points to an engine of unimaginable power. The fundamental difference between Earth's auroras and Jupiter's lies in their source of fuel. Our beautiful northern and southern lights are a gift from the sun, created when charged particles from the solar wind are funneled down our planet's magnetic field lines and slam into the upper atmosphere, causing the air to glow. Jupiter, however, is so far from the sun that the solar wind is relatively weak. It cannot possibly account for the sheer, relentless fury of the Jovian light show. Instead, Jupiter has to create its own particles, drawing power from two incredible internal sources. The first is the planet's own breathtaking rotation. Spinning once every 9 hours and 50 minutes, Jupiter is a gigantic whirlpool of momentum. This rapid spin, combined with the planet's immense magnetic field, creates a powerful electric field that can rip electrons away from molecules and violently accelerate charged particles toward the poles. But the real wild card in this cosmic power plant is a moon that seems worlds away, the violently volcanic Io. Io is caught in a perpetual gravitational tug of war between Jupiter and its other large moons, and this stress heats its interior to the melting point, making it the most volcanically active body in the solar system. Its countless volcanoes constantly spew immense plumes of sulfur and oxygen high into space. This material doesn't just float away, it becomes trapped by Jupiter's powerful gravity and magnetic field, forming a vast, donut-shaped cloud of ionized gas that encircles the planet, known as the Io plasma torus. This torus is a ready-made reservoir of charged particles. Jupiter's magnetic field siphons this material away, channeling it along invisible magnetic highways and accelerating it to nearly the speed of light in a process that is still not fully understood. The result is a self-sustaining circuit where the planet's rotation provides the engine, and its volcanic moon provides the fuel for a light show that has been running non-stop for billions of years. For a long time, scientists assumed this process operated on a grand, systemic scale, accelerating huge populations of particles in a relatively uniform way. But the Juno spacecraft, with its polar orbit, gave us our first close-up view of these auroral ovens, and the data revealed a far more complex and mysterious picture. Juno discovered that alongside the massive main auroral ovals, there are also intricate, small-scale structures known as discrete auroral arcs. These are intense, focused beams of energy, like individual spotlights within the colossal stadium lights of the main aurora. Their existence was a complete surprise and suggests that the acceleration of particles is not a smooth, planet-wide process. Instead, it is likely driven by a series of much smaller, more localized and incredibly powerful interactions within Jupiter's magnetic field. These discrete arcs are believed to be the visible signature of a process called Alfvén waves. Imagine flicking a giant, invisible whip made of magnetic field lines. The wave that travels down the whip carries energy, and when it crashes into the upper atmosphere, it can transfer that energy in a sudden, violent burst, accelerating a specific pocket of particles to incredible speeds and creating a brilliant, isolated arc of light. The presence of these arcs indicates that Jupiter's magnetosphere is crackling with these small-scale energy releases, a turbulent and chaotic environment that our previous models failed to capture. It means that the total power of Jupiter's auroras is not just the sum of one giant engine. but the combined output of millions of these smaller, volcanic explosions happening simultaneously across the poles. This discovery forces us to confront the fact that even our most advanced theories are still only scratching the surface of the complex plasma physics governing this giant's interaction with its space environment. This fundamental lack of a solid surface is perhaps the most mind-bending aspect of the entire planet, a reality that forces us to completely rethink what a world can be. On Earth or on Mars, the concept of a surface is straightforward. It is the ground beneath our feet, a clear boundary between the atmosphere and the solid planet. But on Jupiter, that boundary simply does not exist. Instead, if you were to descend through those beautiful, swirling clouds, you would experience a journey unlike any other. The sky would gradually thicken around you, the hydrogen and helium gas becoming denser and denser, like diving deeper and deeper into an ocean. The temperature would rise dramatically, and the pressure would increase to crushing levels, but you would never hit a seafloor. You would just keep sinking, the gas around you becoming so compressed that it transitions without fanfare into a bizarre, hot liquid. This raises a profound and strangely difficult question. Where does Jupiter's atmosphere end and its interior begin? Where is the surface of a gas giant? The answer is not a line but a zone, and it is governed by one of the most peculiar states of matter known to physics, the supercritical fluid. For any substance, there is a specific combination of temperature and pressure known as its critical point. Below this point, the substance can exist as either a clear-cut liquid or a distinct gas. You can have liquid water and steam, and you can tell them apart. But when you push a substance beyond its critical point, something remarkable happens. The familiar division between liquid and gas completely vanishes. The substance becomes a supercritical fluid, a hybrid phase that has the density of a liquid but the expanding, filling nature of a gas. It can effuse through solids like a gas, yet it can also dissolve materials like a liquid. For the hydrogen and helium that make up most of Jupiter, this critical point is reached at a depth where the pressure is around 12 times the pressure found at the bottom of Earth's Mariana Trench, and the temperature is hotter than the surface of Venus. Once you pass this invisible threshold, the very idea of a surface loses all meaning. You are no longer in a gas or a liquid. You are in a continuous, seething ocean of supercritical fluid. There is no meniscus, no clear line of separation. A spacecraft or a probe descending into this environment would not experience a splash or a landing impact. It would simply note that the fluid outside its hull was becoming steadily denser and hotter, with no single moment marking a transition. This presents an almost philosophical problem for planetary scientists. How do you define the size of a planet that has no solid ground? Astronomers use the point where the atmospheric pressure equals 1 bar. The pressure at sea level on Earth as a conventional reference point for Jupiter's radius. But this is merely a convenient fiction, a way to put a number in a textbook. The real planet extends far above this point into its thin upper atmosphere and infinitely below it into the ever denser interior. Jupiter is a world without a floor. This profound lack of a solid surface is the primary reason why our exploration of Jupiter's depths remains so indirect and fraught with mystery. We cannot send a lander to drill into its core or place a seismometer to listen for Jovian earthquakes. Every probe we have ever sent, like the courageous Galileo atmospheric probe, is doomed to a single fatal mission: to transmit data for as long as it can while being crushed, melted, and vaporized by the increasingly hellish conditions. The Galileo probe survived for about an hour, descending only 150 kilometers, a mere scratch on the face of the giant before its signals were silenced. It provided a priceless snapshot of a single location, but it barely penetrated the outermost layers. To understand what lies beneath, we are forced to become cosmic detectives, relying on remote sensing, gravitational measurements, and sophisticated computer models to infer the conditions thousands of miles down. This incredible challenge is what makes missions like Juno so revolutionary. By meticulously mapping Jupiter's gravity field and magnetic field, Juno allows us to weigh the interior and sense the flows of electrically conductive material deep within, giving us our first real glimpse into the structure of this vast supercritical ocean. The data suggests that the transition to the exotic liquid metallic hydrogen we discussed earlier happens gradually within this supercritical realm. There is no sharp boundary where hydrogen suddenly becomes metallic. Rather, as the pressure mounts, the supercritical fluid's molecules are forced so close together that their electrons can no longer cling to individual atoms and instead break free, creating a sea of charged particles that can conduct electricity, the liquid metal that powers Jupiter's mighty dynamo. The mystery of Jupiter's missing surface is therefore the gateway to understanding its most powerful features, proving that the planet's true nature is not found on a crust, but in the strange and continuous nature of its entire being. Yet for all the grandeur of Jupiter's planet-wide weather systems and its internal dynamo, some of the most astonishing revelations have come from focusing on its most extreme latitudes. When the Juno spacecraft first swung over Jupiter's poles, it revealed a sight so unexpected and geometrically perfect that it seemed almost artificial. Gone were the familiar, chaotic stripes of the lower latitudes. In their place was a breathtakingly organized chaos, a constellation of colossal cyclones arranged with near mathematical precision. At the North Pole, 8 giant storms, each as wide as the entire continental United States, whirled in a tight, polygonal pattern around a single central cyclone. At the South Pole, a similar but distinct configuration featured 5 such cyclones orbiting another central storm. These were not temporary features. They have remained steadfastly in place, their numbers and positions unwavering for the entire duration of Juno's mission. The immediate, baffling question was how such immense, powerful vortices, each packing winds comparable to the most ferocious hurricanes on Earth, could avoid the fate of all storms on our planet, which is to eventually collide and merge into a single, larger system. This stable, polygonal dance defies our basic understanding of fluid dynamics and presents one of the most visually striking mysteries of the Jovian system. The stability of this bizarre polar arrangement likely hinges on a delicate balance of forces unique to the polar environment. One of the most critical factors is Jupiter's breathtaking rate of rotation. The planet's 10-hour spin generates an immensely powerful Coriolis force, the same effect that causes hurricanes on Earth to rotate. But on Jupiter, this force is so strong that it effectively pins atmospheric features in place, preventing them from drifting freely and merging. It creates a rigid, planet-sized atmospheric shell where storms are forced to interact in very specific ways. Imagine trying to push 2 powerful magnets together with their same poles facing. They resist merging due to a repulsive force. A similar phenomenon may be at work with these cyclones. Each storm is a massive, rotating vortex, and the interaction between their swirling flows could create a kind of anticyclonic ring, a buffer zone of spinning wind that acts as a shield, pushing neighboring storms apart and maintaining a respectful distance between them. But rotation alone isn't enough to explain the perfect geometric arrangement. This is where more exotic theories come into play. Some scientists propose that the key lies not in the storms themselves, but in what's happening beneath them. Deep below the visible cloud tops, powerful planetary scale waves, known as Rossby waves, might be propagating through the atmosphere. These are massive, slow-moving waves in the fluid of the atmosphere, analogous to waves in the ocean. It's possible that these underlying waves create an invisible, standing pattern, a template of high and low pressure, that effectively corrals the cyclones into their specific positions at the poles. The storms would then be like marbles rolling in a bowl, trapped in the valleys of this wave pattern, unable to escape their designated slots in the polygonal formation. The different numbers of storms at each pole, 8 in the north, 5 in the south, would then reflect different resonant wave patterns unique to the atmospheric dynamics of each polar region. Another fascinating possibility involves the concept of convection, the same engine that drives Jupiter's banded structure. The poles are regions of intense cooling where heat from the planet's interior finally escapes into space. This could set up a very specific pattern of rising and sinking air. The central polar cyclone might be a massive, persistent upwelling of warm air, while the surrounding cyclones are part of a complex downdraft system. In this model, the entire geometric structure is a self-organizing system, a natural consequence of how heat is distributed and dissipated at the poles. The storms aren't just randomly placed, they are an integral part of the planet's global heat engine, a visible manifestation of the most efficient way for Jupiter to vent its immense internal energy into the cold of space. The stability of the pattern suggests that it represents a state of equilibrium, where the energy feeding the storms is perfectly balanced by the energy lost through friction and other processes. Juno's continued observations will be crucial to determine which of these theories holds the most weight, as even small changes in the storm's intensities or positions could reveal the hidden forces that lock them into their mysterious, beautiful dance. The beautiful, orderly stripes we see from space are driven by jet streams of almost unimaginable power, but for decades, a fundamental question haunted planetary scientists: were these winds merely skin-deep? Imagine the planet's atmosphere as an ocean. We could see the powerful currents racing across its surface, but we had no idea how far down they reached. Were these jet streams just a spectacular surface phenomenon, a thin veneer of weather atop a relatively calm and deep interior? Or did they plunge downward, their roots anchored in the very foundations of the planet? The answer to this question would determine our entire understanding of how Jupiter's weather engine truly operates. This mystery remained unsolvable with telescopes alone. It required a clever, indirect measurement. The Juno spacecraft provided the key by performing a kind of planetary ultrasound. It didn't try to see the winds directly. Instead, it mapped Jupiter's gravitational field with incredible precision. The principle is elegant. If the jet streams were only shallow features, the mass distribution deep within the planet would be almost perfectly symmetrical. But if these flowing bands of atmosphere extended thousands of miles down, they would represent massive rivers of material moving at different speeds. The faster-moving jets would have slightly less mass per volume due to centrifugal force, while the slower-moving regions would be slightly denser. These tiny differences in mass would create minute but detectable wobbles in Jupiter's gravitational field. Juno's delicate measurements of these gravitational anomalies revealed a staggering truth. The jet streams are not superficial. They are massive structures that extend or are rooted to a depth of about 1,800 miles or 3,000 kilometers beneath the cloud tops. To grasp the scale of this discovery, consider that this depth is roughly equivalent to the width of the entire United States. These are not gentle breezes. They are planet-scale conveyor belts of hydrogen and helium gas, reaching through an atmospheric layer that represents about 1% of Jupiter's total mass. That 1% may sound small, but on a planet this size, it encompasses a volume of material greater than that of our entire Earth. This finding fundamentally rewrote the textbook on gas giants. It proved that Jupiter's magnificent weather system is not a thin film on top of the planet, but is inextricably linked to its deep interior. The energy driving those bands must come from within, not just from the sun above. This revelation, however, solved one mystery only to create a far more profound and difficult one. What possible mechanism can sustain such powerful, organized flows so deep within the planet? On Earth, our weather is driven by solar heating and is confined to a very thin shell because we have a solid surface that acts as a hard boundary. Jupiter has no such surface. Below the clouds, the atmosphere simply gets denser and hotter. eventually turning into that exotic supercritical fluid and then into liquid metallic hydrogen. The idea of a coherent wind persisting in such a strange, dense, and electrically conductive environment is a monumental challenge to our understanding of fluid dynamics. One leading theory points to the internal heat generated by the planet itself as the ultimate power source. This heat, rising from the deep interior, must find a way to escape. It does so through convection, the same process that causes water to boil in a pot. On a spinning sphere like Jupiter, this rising and sinking motion becomes organized by the planet's powerful rotation into the banded structure we see. The jet streams may be the visible tops of deep, cylindrical rolls of convection that extend all the way down to that 1,800-mile mark, where some unknown barrier or change in the physical properties of the interior finally disrupts them. In this model, the entire outer shell of Jupiter is a single, interconnected weather machine. Another, more exotic possibility involves the influence of Jupiter's powerful magnetic field. Deep down, where hydrogen becomes a liquid metal, the motions of this electrically conductive fluid are constrained by the magnetic field lines that permeate it. It's possible that the jet streams we see at the surface are actually a surface expression of deeper flows within the metallic hydrogen layer itself. The magnetic field could act like a set of invisible rails, guiding and stabilizing these deep currents and effectively coupling the weather in the outer atmosphere to the dynamics of the interior dynamo. This would create a unified system where the magnetic field and the atmospheric winds are two sides of the same coin, an interconnected phenomenon that has been operating in sync for billions of years. The true nature of this deep-seated engine remains one of Juno's most significant puzzles, a clue that the atmosphere and the interior of this giant world are far more intimately connected than we ever imagined. The discovery that Jupiter's jet streams plunge thousands of miles deep forces us to confront a completely new reality about how weather works on a gas giant. It shatters the old idea of a simple weather layer, a thin, sun-driven skin of activity sitting on top of a quiet, homogeneous interior. Instead, we are looking at a planetary system where the dazzling surface patterns are directly wired into the planet's deepest energies. This profound connection points to a single, overwhelming power source, Jupiter's own internal furnace. Unlike Earth, where the sun's uneven heating drives our winds and storms, Jupiter's weather is primarily powered from within. The immense heat left over from its formation and generated by its ongoing gravitational contraction provides the energy that drives the entire atmospheric engine. This internal heat creates a continuous cycle of convection, a churning motion that is the true architect of Jupiter's appearance. Picture a pot of water slowly boiling on a stove. The water at the bottom, closest to the heat source, warms up, becomes less dense, and rises. When it reaches the surface, it cools, becomes denser, and sinks back down, only to be reheated and rise again. Now, imagine this process happening on a planetary scale, within an ocean of hydrogen and helium that is tens of thousands of miles deep, and all of it spinning at a dizzying rate. Jupiter's rapid rotation organizes this colossal, planet-wide boiling into the parallel bands we see. The rising arms of these convection cells become the bright zones, while the sinking arms become the dark belts. The powerful jet streams are the high-speed currents at the boundaries between these massive, rolling cylinders of rising and falling gas, a natural consequence of this organized churning. This new understanding dramatically challenges the previous models and redefines what it means for a planet to rotate. For a long time, scientists wondered if the different cloud bands, moving at different speeds, indicated that the entire interior of Jupiter was rotating in a series of nested cylinders, like a set of gears inside a clock. But Juno's gravity measurements suggest something far more surprising. Beneath a depth of about 1,800 miles, the planet appears to rotate almost as a rigid body. It's as if the tumultuous, banded atmosphere we see is just a relatively thin, dynamic shell gliding over a much more uniform and coherently spinning interior. The deep winds, for all their immense power and depth, are actually a surface phenomenon when viewed against the full scale of the planet, a spectacular, complex film on top of a giant that turns in near unison at its heart. This transition point, the boundary where the jet streams finally vanish, is one of the great frontiers in planetary science. What happens at this depth to finally dampen these powerful flows? The leading hypothesis involves the increasing density and the growing influence of Jupiter's powerful magnetic field. As we descend, the pressure and temperature rise to such extremes that the hydrogen gas transitions into that exotic liquid metallic state. This fluid is an excellent electrical conductor, and its motions are strongly constrained by the magnetic field lines that permeate it. It's possible that the magnetic field acts as a brake or a guide, effectively locking the deep interior into a more uniform rotation and preventing the kind of differential motion we see in the outer atmosphere. The jet streams we observe, therefore, may be the last magnificent expression of convection in the molecular hydrogen layer before the physics of the interior becomes dominated by the magnetism of the metallic hydrogen below. This redefines our entire view of atmospheric dynamics, showing that on a gas giant, the weather is not just an atmospheric affair, but a direct dialogue between the planet's hot heart and its powerful magnetic soul. This gravitational imbalance is a direct window into the planet's soul, revealing that the hidden currents of mass deep within Jupiter are not flowing in a uniform, predictable way. On a perfectly symmetrical planet, where mass is evenly distributed from the core to the cloud tops, the gravitational field would be smooth and even. But Juno found the opposite. This north-south asymmetry means that there is more mass concentrated in one hemisphere than the other. Picture Jupiter not as a perfectly round ball, but as a slightly lopsided one, perhaps a bit heavier on one side. This isn't due to a bump on the surface. There is no surface to have a bump. Instead, this uneven pull is caused by profound differences in how material is churning and settling thousands of miles beneath the clouds we can see. The planet's gravity is essentially a map of its hidden mass, and Juno's map shows a startlingly distorted world. So, what specific internal arrangements could be causing this lopsidedness? Scientists are investigating several compelling possibilities, all of which point to a far more complex and dynamic interior than we ever imagined. One leading theory focuses on the very jet streams we just discussed. We now know these atmospheric rivers plunge over 1,000 miles deep, but what if their depth is not the same everywhere? It's possible that the jet streams in Jupiter's northern hemisphere extend slightly deeper into the planet than their counterparts in the south. Even a difference of a few dozen miles, when applied to flows of gas that are thousands of miles wide and moving at incredible speeds, would represent a significant redistribution of mass. The hemisphere with the deeper flows would have a slightly greater concentration of mass, and therefore a slightly stronger gravitational pull, creating the exact kind of asymmetry that Juno detected. Another, even more profound explanation involves the bizarre nature of Jupiter's diluted core. Recall that the planet's heavy elements are not concentrated in a neat, central ball, but are instead mixed and stirred into a vast region of the interior. This fuzzy core might not be fuzzy in a symmetrical way. The material making up this diluted core, the rocks and metals that formed the planet's original seed, could be distributed unevenly. Perhaps a larger fraction of this heavy material has settled or been stirred into the northern hemisphere, making that half of the planet intrinsically denser. This would be like having a clump of lead shot mixed into one side of a water balloon. That side would sag a little more, its gravitational pull slightly stronger. This scenario suggests that the cataclysmic impact thought to have shattered Jupiter's early core did not mix the debris evenly, leaving a lasting billion-year fingerprint on the planet's gravitational field. The true cause likely involves a combination of these factors, a complex interplay between the deep atmospheric weather and the fundamental structure of the interior. The asymmetry Juno measured is not a small anomaly, it is a fundamental feature of the planet. This tells us that the internal dynamics of a gas giant are not the same in all directions. The forces of rotation, convection, and magnetism may operate with different intensities or patterns in the north versus the south, leading to these large-scale imbalances. This gravitational mystery forces us to abandon any simple, neat model of Jupiter's interior. Instead, we must see it as a world of profound complexity, where the flows that power its beautiful surface stripes and the distribution of its ancient building blocks have created a hidden architecture that is quite literally unbalanced. Just when we thought we were beginning to understand the broad strokes of Jupiter's atmospheric circulation, the planet presented us with a chemical puzzle that seemed to defy logic. For years, telescopic observations had hinted at a strange anomaly near the equator, a pronounced depletion of ammonia. In the grand chemical symphony of Jupiter's atmosphere, ammonia is a lead player. It's the compound that condenses into the bright, white ice crystals that give the zones their brilliant color. So, to find a band around the planet's middle that was significantly poorer in this key ingredient was baffling. The simplest explanation seemed to be a process akin to weather on Earth. Perhaps in this specific region, the ammonia was simply raining out. The idea was that moist, ammonia-rich air would rise, cool, and form ammonia ice crystals that would then fall back down as a kind of planetary-scale snow shower, effectively draining the upper atmosphere of its ammonia and depositing it in the warmer layers below. It was a neat and tidy theory, but like so many things on Jupiter, the reality turned out to be far more complex and spectacular. The truth was revealed by Juno's unique ability to peer deep beneath the visible cloud tops. Its microwave radiometer can sense the thermal emission coming from different depths within the atmosphere, effectively allowing it to create a three-dimensional chemical map. When scientists pointed this powerful instrument at the supposedly ammonia-poor equatorial region, they expected to see a deep, dry column where the ammonia had all sunk. Instead, they discovered the opposite. The data unveiled a massive, concentrated plume of ammonia rising from the deep atmosphere like a colossal geyser. This wasn't a region of depletion at all. It was a site of intense, focused upwelling. The ammonia wasn't missing. It was simply being transported in a way we never anticipated. The mystery instantly transformed from where did the ammonia go to what incredible force is creating this ammonia fountain. This discovery pointed to a phenomenon that is both violent and beautifully organized, a megastorm or a cluster of enormous storm systems operating deep within Jupiter's atmosphere. The leading theory suggests that the plume is the visible signature of a powerful atmospheric cell, similar to the convection that drives thunderstorms on Earth, but operating on a scale that dwarfs our entire planet. In this scenario, the ammonia-rich plume is the rising arm of a planetary heat engine. Warm, moist air from the deep interior, carrying a high concentration of ammonia vapor, is buoyant and surges upward with immense force. As it rises, it cools, and some of the ammonia condenses out, which could explain the relative lack of it in the immediate upper levels. The ammonia is being carried so rapidly upward that it hasn't had time to fully saturate the local environment. This rising column would eventually hit a barrier in the upper atmosphere, spread out, and then sink back down in the surrounding areas, creating a continuous cycle. What makes this plume so mysterious is its concentrated, enduring nature. On Earth, even the largest thunderstorms are temporary and localized. Jupiter's ammonia plume, by contrast, appears to be a stable, large-scale feature. This suggests it is not a random event but a fundamental part of the planet's equatorial circulation, likely stabilized by Jupiter's powerful rotation and the unique conditions at the equator. The Coriolis force, which gives hurricanes their spin on Earth, behaves differently at the equator, where its effect is minimized. This may allow for the formation of these massive, relatively straight updrafts that can channel material from the deep interior with astonishing efficiency. The plume acts like a cosmic elevator, rapidly transporting not just ammonia but heat and other chemicals from the hidden depths to the higher reaches of the atmosphere. The existence of this fountain forces a major revision of our models. It shows that Jupiter's atmosphere is not just a layered system of belts and zones. It is punctured by these massive, vertical transporters that directly link the surface whether we see to the abyssal depths we cannot. This ammonia plume is a direct pipeline from the planet's hot interior, a mechanism for venting heat and redistributing chemicals on a global scale. Understanding what drives and sustains this plume is key to mapping the complete life cycle of materials in Jupiter's atmosphere and reveals a level of dynamic complexity in atmospheric physics that we are only just beginning to appreciate. And now we turn our attention from the planet's churning atmosphere to a feature that often gets overlooked in the shadow of its more famous cousin, Jupiter's own ring system. When we picture rings around a planet, our minds naturally leap to the breathtaking, icy brilliance of Saturn. Jupiter's rings, by contrast, are ghostly and faint, a whisper of dust so delicate that they remained completely hidden from Earth-based telescopes and were only discovered by the Voyager 1 spacecraft in 1979. Their subtle nature, however, makes them no less fascinating. In fact, their very faintness is the key to a compelling mystery about their origin and their stark difference from the glorious rings of Saturn. The primary source of Jupiter's main ring is now widely understood to be a case of cosmic collateral damage. This ring doesn't consist of vast, bright chunks of ice. Instead, it is composed of incredibly fine, dark dust particles, most no larger than the particles in cigarette smoke. The leading theory points to Jupiter's two small inner moons, Metis and Adrastea. These tiny worlds orbit perilously close to the planet, well within the main ring's boundary. They are constantly bombarded by micrometeorites, tiny specks of space debris traveling at tremendous speeds. Each microscopic impact acts like a miniature explosion, blasting dust and debris off the surfaces of these moons. This ejected material doesn't just float away, it becomes trapped by Jupiter's powerful gravity, entering into orbit around the planet and forming the thin, diffuse band we observe as the main ring. It's a continuous, slow-motion demolition project where the rings are constantly being replenished by this steady rain of impacts. Yet, the structure of this ring system holds deeper puzzles that go beyond a simple dusty band. Extending inward from the main ring toward the planet's cloud tops is a curious feature known as the halo ring. This is a thicker, torus-shaped cloud of dust that seems to float above and below the plane of the main ring. Its existence is a direct clue to the powerful invisible forces at work around Jupiter. The particles in the halo ring are likely even smaller and lighter than those in the main ring. Because of their tiny size, they are exquisitely sensitive to electromagnetic forces. Jupiter's immense magnetic field, the strongest in the solar system, exerts a push and pull on these charged dust grains, nudging them out of the flat orbital plane and causing them to oscillate, creating the halo's distinctive puffed-up appearance. It's a visible testament to the planet's magnetic influence shaping its immediate environment. On the opposite side, extending outward from the main ring, are the gossamer rings. These are even fainter and more tenuous, and they are directly linked to two other small moons, Amalthea and Thebe. The dust ejected from these moons spreads out to form wide, disc-like rings that are remarkably flat, mirroring the orbital paths of their parent bodies. This gives the entire ring system a layered, structured quality, with each component acting as a fingerprint for the moon that supplies it. This connection provides a crucial insight. Unlike Saturn's massive, ancient rings, which may be remnants from the planet's formation, Jupiter's rings are a contemporary feature, a dynamic and ever-changing system that depends entirely on the ongoing existence of these source moons. This brings us to the central comparative mystery. Why are Jupiter's rings so dim, dark, and dusty compared to the brilliant ice of Saturn's? The answer lies in the different environments around the two giant planets. Saturn orbits far enough from the Sun that water ice is stable and highly reflective, acting like countless tiny mirrors. Jupiter, while still in the outer solar system, is closer to the Sun and subject to a more intense flux of charged particles trapped in its own radiation belts. This harsh environment has a darkening effect. The dust particles in Jupiter's rings are likely coated with dark, carbon-rich material or iron-bearing silicates, similar to the surfaces of the moons they come from. Furthermore, the constant bombardment by radiation likely causes a process called sputtering, where high-energy particles literally knock atoms off the dust grains, further darkening them over time. The rings are dark because they exist within a celestial sandblaster. The final enigma is one of maintenance and balance. The rings are in a constant state of flux. Dust is always being added from the moons, but it is also always being lost. Individual dust particles don't last forever. They can spiral inward toward the planet due to drag or be pushed out by the pressure of sunlight. The very fact that we see a stable ring system means there is a delicate equilibrium between the rate of dust production and the rate of dust loss. If the micrometeorite bombardment were to cease, the rings would likely dissipate within a relatively short period, perhaps thousands or millions of years, a blink of an eye in cosmic terms. Their continued existence is therefore a live broadcast of the ongoing activity within the Jovian system, a fragile, dusty tapestry woven by the relentless interplay between unseen impacts, planetary gravity, and the unforgiving fury of radiation. But our journey into the Jovian system's mysteries must also confront a puzzle that defies expectations in a place we might least expect it, high above the violent cloud tops in a region that should be frigidly cold. This is the mystery of Jupiter's inexplicably hot upper atmosphere, a conundrum so baffling it's been dubbed the planetary energy crisis. Imagine stepping away from a campfire on a cold night. The further you get from the flames, the colder you become. By that same logic, the upper atmosphere of a planet, being the most distant layer from the internal heat source and receiving only a faint trickle of sunlight due to its great distance from the Sun, should be intensely cold. For Jupiter, models predict its thermosphere should be around -150 degrees Celsius. Yet when we measure it, the temperature soars to a sizzling 700 degrees Celsius or more. It's as if you walked away from the fire and suddenly found yourself in an oven. The fundamental question is simple: where is all this excess heat coming from? Scientists have been investigating several compelling theories, each pointing to a different powerhouse operating within the Jovian system. One prominent idea involves the damping of atmospheric gravity waves. This doesn't refer to gravitational waves in space-time, but to literal waves that travel through the atmosphere itself, much like waves on the ocean. Deeper within Jupiter, the colossal thunderheads and violent storm systems generate massive ripples that propagate upward. As these waves travel into the thinner upper atmosphere, they break, much like an ocean wave crashing on a shore. This braking action transfers their energy of motion into thermal energy, effectively heating the thin gas around them. It's a process that adds heat from below, supplementing the meager warmth provided by the distant Sun. A second, and perhaps more significant, theory points directly to Jupiter's crown of power, its auroras. We've already seen how the auroras are immense funnels of energetic particles slamming into the atmosphere at the poles. The incredible friction and collisions generated by this particle precipitation create intense heat, a process known as Joule heating. The logical assumption was that this polar heating would be trapped near the poles, creating hotspots while leaving the equatorial regions cold. However, recent observations suggest something remarkable is happening. It appears that this tremendous heat generated at the poles doesn't just stay put. Instead, it may be channeled away by powerful global wind systems, effectively redistributing the thermal energy across the entire planet. Think of it as a planetary-scale heating system, where the furious energy of the auroras is pumped from the poles toward the equator, warming the entire upper atmosphere in the process. This would make the auroras not just a spectacular light show, but the primary thermostat for the planet's high-altitude weather. Yet, even when we combine these potent mechanisms, the breaking of atmospheric waves and the global distribution of auroral heat, there's a sense that the energy budget might still not fully balance. This has led researchers to consider even more exotic contributors. The sheer power of Jupiter's magnetic field itself may play a direct role, as its constant fluctuations can induce electrical currents in the atmosphere that generate additional heat. Another possibility involves the planet's immense magnetosphere, which acts as a trap for incredibly energetic charged particles. Sometimes these particles can precipitate down into the atmosphere not just at the poles, but in more random events, providing sudden, intense bursts of heating all over the planet. The emerging consensus is that no single silver bullet solves the energy crisis. Instead, the scorching temperatures are almost certainly the result of a complex and synergistic combination of all these processes working in concert. The upper atmosphere is a place where heat from below, power from the magnetic field, and energy from the moons all converge, creating a thermal environment that is far more dynamic and interconnected than we ever imagined. Moving from the searing heat of the upper atmosphere, we descend into the tempestuous heart of Jupiter's weather, where another phenomenon shares a terrifying familiarity with our own world: lightning. The very word conjures images of brilliant forks splitting the sky, but on Jupiter, this force of nature is elevated to an almost apocalyptic scale. The lightning bolts that rage within those swirling clouds are not merely impressive, they are monsters packing hundreds of times the energy of their terrestrial counterparts. If you could stand safely amidst a Jovian thunderstorm, a single flash would not just illuminate the sky, it would be a blinding, deafening explosion of raw power. Yet, for all their shared ferocity, the story of where and how this lightning forms on Jupiter is a tale of profound difference, a clue that the planet's atmospheric engine operates by a set of rules entirely its own. On Earth, the recipe for lightning is relatively straightforward and intimately tied to our geography. The sun's uneven heating creates warm, moist air that rises over land masses, forming massive cumulonimbus clouds. Inside these clouds, interactions between updrafts and downdrafts, along with collisions between ice crystals and water droplets, separate electrical charge. The lighter, positively charged ice crystals are carried to the top of the cloud, while the heavier, negatively charged particles sink to the bottom. When the difference in charge becomes too great, the atmosphere can no longer act as an insulator, and a gigantic spark. Lightning bridges the gap either within the cloud, between clouds, or from the cloud to the ground. Our planet's lightning is predominantly a land-based phenomenon, fueled by the rapid heating of continents. For decades, scientists assumed a similar process would be at work on Jupiter. They predicted that the strongest convection, and therefore the most intense lightning, would be found near the equator, where the sun's energy is most concentrated. This seemed like a safe bet, a simple extension of earthly physics to a larger canvas. The Voyager missions in the late 1970s did indeed detect lightning flashes, seemingly confirming this idea. But when NASA's Juno spacecraft entered a polar orbit, giving it an unprecedented view of the high latitudes, its sensitive instruments picked up something that turned this entire theory on its head. Juno's microwave radiometer was listening for the radio wave bursts, or spherics, that are the unmistakable signature of lightning discharges. To the astonishment of the science team, the data revealed a cacophony of strikes. But they weren't concentrated at the equator. The vast majority of this electrical activity was booming near the poles. This polar preference is the central mystery of Jovian lightning. Why would a planet with an internal heat source so powerful that it dwarfs solar heating generate its most intense electrical storms in its coldest, darkest regions? The answer forces us to abandon the sun-centric model and look instead to the unique atmospheric circulation and chemistry of the giant world. The key lies in what provides the stability for thunderstorms to develop. On Jupiter, the equator is a region of powerful, stable, east-west jet streams. This organized horizontal flow may actually suppress the large-scale vertical convection needed to build the towering thunderheads that generate lightning. The atmosphere is moving so fast laterally that it doesn't have the opportunity to boil upwards with the same ferocity. The poles, by contrast, are a different kind of chaotic. Freed from the constraining influence of the strong equatorial jets, the atmosphere at high latitudes is able to convect more freely. The internal heat from Jupiter's core, which drives the entire weather system, finds a more direct path to escape into space at the poles. This sets up powerful, sustained vertical currents, colossal updrafts and downdrafts that are perfect for brewing planet-sized thunderstorms. But there's a second, even more crucial piece to this puzzle, and it involves a surprising ingredient: ammonia. On Earth, the charge separation in clouds relies heavily on the interactions between water and ice. On Jupiter, the process appears to be more complex, involving a slushy mixture of water and ammonia. Ammonia acts as an antifreeze, preventing water droplets from freezing solid even at the frigid temperatures found in Jupiter's upper cloud decks. This creates a mushy, partially frozen state where water and ammonia water droplets can coexist and collide with ice crystals more effectively, enhancing the friction that separates electrical charge. This antifreeze effect might be the secret ingredient that makes polar lightning on Jupiter not just possible, but commonplace, revealing an atmospheric electrical engine fundamentally unlike anything we experience on our own world. While the powerful jet streams and immense storms define Jupiter's power, its appearance is not a fixed portrait but a living, shifting canvas. One of the most compelling long-term observations is that the planet's vibrant colors and the distinctness of its iconic bands undergo dramatic transformations over decades. The most famous of these is the strange case of the South Equatorial Belt, a broad, dark band that has on several recorded occasions simply vanished from view. To astronomers peering through telescopes, a key feature of the planet's face would fade into the background color of the zones, only to mysteriously return months or years later, often accompanied by intense, darkening outbreaks. This isn't a trick of the light, it is a planet-scale metamorphosis, and the driving force behind these large-scale color variations remains an active area of investigation. The leading hypothesis for these changes centers on the complex interplay between the different cloud decks that make up Jupiter's atmosphere. Imagine the atmosphere as a layered cake. The highest visible layer is composed of bright, white ammonia ice clouds. Beneath that lies a deeper deck of clouds, likely made of ammonium hydrosulfide, which has a reddish-brown hue. Deeper still, there may be clouds of water ice. The visibility of these deeper, darker clouds is what gives the belts their characteristic color. The fading of a belt like the South Equatorial Belt is thought to occur when the upper, white ammonia clouds thicken and spread, effectively forming a high-altitude fog that obscures the darker, more colorful cloud layers below. It's as if a brilliant white veil has been drawn across the planet's deeper atmospheric features. But what causes this veil to form? The process is likely driven by powerful planetary-scale waves that propagate through the Jovian atmosphere. These are not waves in water, but massive, slow-moving oscillations in the density and temperature of the air itself. When these waves converge in a particular region, they can force a widespread upwelling of air. This rising column carries ammonia gas from the warm depths upward into the cold upper atmosphere. There, the gas condenses rapidly, forming a thick, bright overcast of fresh ammonia ice crystals that camouflages the darker belts. The return of the belt's color coincides with a shift in this pattern, where the wave activity subsides and the prevailing downdrafts in the belt region reassert themselves. These sinking currents clear away the high ammonia haze, allowing us to see the darker, deeper clouds once again. This cyclical process suggests that Jupiter's weather operates on rhythms far longer and more complex than our own seasonal patterns. An alternative, and not mutually exclusive, theory involves the upwelling of different chemical compounds from the abyss. The changing colors might not just be about hiding or revealing cloud decks, but about altering the chemical recipe of the clouds themselves. The powerful convection that drives Jupiter's weather could be sporadically tapping into reservoirs of different chemicals located at varying depths. A particularly vigorous uprising might bring forth a richer mixture of sulfur or phosphorus compounds from the deep interior. When these compounds are exposed to ultraviolet light from the sun, they can undergo photochemical reactions, creating new complex molecules, tholins, that possess a distinctly different color palette. A belt might fade not just because it's covered, but because the chemical agent that gives it its dark color has been temporarily depleted or altered, only to be replenished when the deep atmospheric circulation shifts once more. These grand-scale changes are more than just an atmospheric curiosity. They are a vital clue to understanding the interior workings of the giant planet. The fact that these transformations can encompass a band that is wider than our entire planet and persist for months or years indicates that they are driven by deep-seated forces. They are the surface expression of immense heat and momentum being redistributed within the planet's fluid interior. By monitoring these color variations, astronomers are essentially taking the pulse of Jupiter's global circulatory system. Each fade and return is a chapter in the story of how this world manages its incredible internal energy, a dynamic and complex weather system that we are only just beginning to decode, reminding us that even after centuries of observation, the King of Planets still has the power to surprise us. Just when you thought Jupiter's atmospheric behavior couldn't get any more peculiar, we encounter a phenomenon that seems to defy basic logic, one that plays out in the fleeting, inky black shadows cast by its moon. Picture this celestial ballet. One of Jupiter's large moons, like the volcanic Io or the massive Ganymede, glides directly between the giant planet and the Sun. For a brief period, a patch of Jupiter's cloud tops, perhaps large enough to swallow our entire planet, is plunged into a profound and sudden darkness. On any other world, on Earth for example, stepping into a shadow brings an immediate and noticeable chill as the direct source of warmth is blocked. But on Jupiter, the opposite occurs. Instruments on spacecraft have detected a strange and immediate response. The temperature within the shadowed area actually rises. These are the baffling hot shadows of Jupiter, a momentary warming that highlights just how alien the atmospheric physics on a gas giant can be. The explanation for this counterintuitive event is a fascinating lesson in energy balance. Jupiter's upper atmosphere is a constant battleground between competing sources of energy. On one side, you have the meager but constant input of sunlight. On the other, you have the colossal upwelling of heat from the planet's own internal furnace. Normally, these forces reach a kind of stalemate, creating a stable temperature regime. Sunlight doesn't just provide warmth, it also drives complex chemical reactions high in the atmosphere. Specifically, sunlight provides the energy needed to break apart certain molecules like methane and hydrocarbons in a process known as photodissociation. These chemical reactions are endothermic, meaning they absorb heat from their surroundings in order to proceed. Think of it as a natural, planet-wide air conditioning system that is powered directly by sunlight. When a moon's shadow sweeps across this delicate balance, it doesn't just turn off the heat, it flips a switch on the entire atmospheric system. The sudden absence of sunlight immediately halts these cooling chemical reactions. The atmospheric air conditioning system shuts down, but the shadow does nothing to stop the relentless upward flow of heat from Jupiter's deep interior. With the primary cooling mechanism disabled, the internal heat, which is always present and vastly more powerful than the energy received from the distant sun, quickly becomes the dominant force. This trapped heat has nowhere to go but to cause a rapid and measurable temperature spike in the shadowed region. It's as if you were in a room with a powerful fan blowing on a heater, keeping it cool, and someone suddenly unplugged the fan. The room would heat up rapidly, not because the heater got stronger, but because the cooling agent was removed. While this general principle is understood, the precise chemical recipe behind this phenomenon remains an active and complex puzzle. Scientists are diligently working to identify the exact molecules involved in this rapid cooling and heating cycle. The primary suspect is methane, which is abundant in Jupiter's atmosphere. When ultraviolet sunlight hits methane molecules, it can break them apart, and the recombination of those fragments into new, more complex hydrocarbons likely absorbs a significant amount of ambient heat. Other chemicals, like acetylene, are also under investigation for their potential role in this atmospheric thermostat. The challenge is that the effect is so temporary. The shadow passes in a matter of minutes, and the atmosphere quickly returns to its previous state once sunlight is restored. This makes it incredibly difficult to get detailed spectral readings of the exact chemical changes occurring during the event. The existence of these hot shadows provides a uniquely powerful tool for planetary scientists. It acts as a natural laboratory experiment, allowing them to observe how Jupiter's atmosphere responds to a sudden, localized change in energy input. By studying the rate and magnitude of the temperature change, researchers can infer crucial details about the efficiency of the atmospheric circulation and the rate at which heat is transported from the deep interior to the upper layers. This fleeting event reveals the invisible hand of Jupiter's internal power, demonstrating that even when the sun is momentarily blocked, the planet's own immense energy is more than capable of shaping its environment in ways that continue to surprise and challenge our understanding. This staggering gravitational dominance extends far beyond its current orbit, reaching back in time to the very dawn of our solar system, and it may have choreographed the most critical dance in our planet's history. This brings us to one of the most revolutionary ideas in modern planetary science, the grand tack hypothesis. The word tack here comes from sailing, referring to a change in direction. The theory proposes that the Jupiter we see today, majestically orbiting far from the Sun, was not always in this position. In its infancy, just a few million years after the Sun ignited, Jupiter began its life much closer to our star. As it formed from the primordial disk of gas and dust, gravitational interactions with that disk caused the giant planet to begin a slow, relentless migration inward, like a cosmic whirlpool being drawn toward a drain. This journey brought a young, hungry Jupiter perilously close to the region where the inner, rocky planets Mercury, Venus, Earth, and Mars would one day form. This inward spiral, however, was not destined to continue all the way to the Sun. The grand tack model introduces a savior, or at least a gravitational partner in this drama, Saturn. As Jupiter migrated inward, Saturn, forming slightly later and further out, began its own inward journey. But because Saturn is less massive, it migrated faster through the disk. Eventually, it caught up to Jupiter, and the two giants became locked in a special gravitational resonance. This resonance created a powerful, combined gravitational influence that began to clear a wide gap in the protoplanetary disk. The physics of this interaction then reversed their migration. Like two objects linked together, they changed tack and began to migrate back outward, with Jupiter leading the way, eventually settling into the orbits we see today. This grand billion-year journey inward and then back outward is the tack that may have defined the solar system's architecture. The implications of this celestial reversal are profound, and they answer some of the most puzzling questions about our own world. Before this idea, scientists struggled to explain why the inner solar system is so clean and contains such relatively small planets. The standard model of planet formation suggested that there should have been enough material near Earth's orbit to form a much larger world, a so-called super-Earth, which is a common type of planet we see around other stars. The Grand Tack hypothesis provides an elegant and dramatic solution. As Jupiter marched inward and then back out, its immense gravity would have acted like a colossal snowplow. It would have scattered the vast majority of the planet-building material in the inner solar system, either flinging it outward into the Kuiper belt or hurling it completely into the Sun. This left behind a sparse collection of smaller planetary embryos, which eventually collided and merged to form the modestly sized rocky planets we have today. In a very real sense, Jupiter's migration may be the reason Earth is the size it is, and not a massive, uninhabitable super-Earth, but Jupiter's role may have been even more crucial than simply clearing the neighborhood. It might have been the very delivery service that brought the ingredients for life to our doorstep. The early inner solar system was a hot, dry place where water ice could not survive close to the Sun. The water that fills our oceans must have come from the colder outer regions. The Grand Tack model suggests that when Jupiter swung back outward, its gravitational influence hurled a vast population of water-rich asteroids and comets from the outer disk into the inner solar system. This would have been a cataclysmic bombardment, a rain of icy celestial bodies that pummeled the young, rocky protoplanets. This event, often called the Late Heavy Bombardment, while violent, may have been the mechanism that seeded Earth with its life-giving water. So, Jupiter's ancient migration could be the reason our world is a blue marble, a water world instead of a barren desert. Of course, the Grand Tack hypothesis is just that, a hypothesis. It is a compelling story that fits many of the facts, but confirming an event that occurred over 4 billion years ago is incredibly difficult. The primary evidence comes from sophisticated computer simulations of the early solar system. When researchers program the physics of planetary migration into these models, the Grand Tack scenario consistently produces a solar system that looks remarkably like our own, with small inner planets and a clear separation between the rocky and gaseous worlds. The alternative, that the planets formed more or less in their current locations, has a much harder time replicating the structure we observe. The mystery, then, is to find more tangible proof. Astronomers search for clues in the precise orbital arrangements of asteroids, in the chemical compositions of meteorites that may be remnants of that scattered material, and in the study of young planetary systems around other stars where we might catch a gas giant in the act of migrating. Unraveling this ancient mystery is not just about understanding Jupiter's past. It is about discovering the pivotal events that made our own existence possible, revealing that the King of Planets may have once been the architect of our cosmic home. While the polar cyclones present a geometric puzzle at the highest latitudes, another, equally captivating atmospheric arrangement exists further south, a feature so elegant it has earned the name the String of Pearls. Imagine looking at Jupiter's southern hemisphere and seeing a perfect necklace of brilliant white ovals, each a colossal storm in its own right, evenly spaced along the dark ribbon of the South Temperate Belt. These are not transient weather patterns. Some of these pearly vortices have been observed for decades, circling the planet in a seemingly choreographed dance. Their longevity and perfect spacing pose a fascinating mystery. In an atmosphere defined by chaotic mergers and violent interactions, how do these massive storms avoid colliding and instead maintain their individual identities for such astonishing periods of time? The secret to the stability of the String of Pearls appears to lie in the presence of powerful, invisible forces shaping the Jovian atmosphere, specifically planetary scale waves known as Rossby waves. On Earth, Rossby waves are massive meanders in the high-altitude jet stream that influence our weather patterns. On Jupiter, these waves operate on a much grander scale. They are slow-moving waves in the fluid of the atmosphere itself, driven by the planet's rapid rotation and the variation in the Coriolis force with latitude. Think of them not as waves on an ocean, but as rhythmic, undulating pulses in the very fabric of the atmospheric currents. Scientists believe that the string of pearls is the visible manifestation of such a wave. The bright, white oval storms form at the crests of this underlying wave pattern, where the atmospheric flow creates stable points of low pressure that act like celestial docking ports for these gigantic vortices. This wave theory elegantly explains why the pearls don't merge. Each storm is essentially trapped in a trough of the Rossby wave, like a bead on an invisible wire. The interaction between the swirling flow of one vortex and the atmospheric currents generated by the wave pattern creates a protective barrier around each oval. When two storms drift close to one another, their rotating winds and the surrounding flow established by the wave push them apart, maintaining a respectful distance. It's a delicate balance of forces, the storm's own rotational energy versus the guiding hand of the planetary wave. This is similar to the mechanism proposed for the polar cyclones, but it operates in a different latitudinal band where the specific dynamics of the jet streams and the Coriolis effect create this unique, pearl-like arrangement instead of a polygon. The enduring nature of the string of pearls tells us something profound about Jupiter's weather. Their multi-decade stability suggests that the Rossby wave pattern that underpins them is itself incredibly stable, a permanent feature of the planet's atmospheric circulation. This points to a level of large-scale organization within the apparent chaos that we are only beginning to appreciate. The pearls are not random accidents, they are reliable landmarks in a constantly churning sky, indicating the presence of these deep, rhythmic pulses that structure the planet's weather on a global scale. Their continued observation allows scientists to monitor the health and behavior of these fundamental atmospheric waves, providing a long-term gauge for understanding how Jupiter's climate operates over time scales far longer than a human lifetime. And now we venture beyond visible light and into the realm of the unseen, where Jupiter reveals itself not as a silent giant, but as a roaring broadcaster in the cosmos. This is the mystery of Jupiter's radiometric brightness. The planet is an incredibly powerful source of radio waves, a type of low-frequency light invisible to our eyes but easily detectable by our radio telescopes. This isn't a gentle hum, it's a series of intense, sporadic bursts that can outshine the sun in the radio portion of the spectrum. The source of this radiation is a dramatic dance of high-energy physics. Electrons trapped within Jupiter's immense magnetic field are forced to spiral along the invisible field lines. This spiraling motion causes them to emit energy in the form of radio waves, a process known as synchrotron radiation. It's a natural particle accelerator on a planetary scale. The plot thickens enormously when we discover that this radio broadcast is not a solo performance. For decades, astronomers noticed a strange pattern. The most powerful bursts of radio noise seemed to be tied to the orbital position of the volcanic moon, Io. This was a stunning connection, linking a distant moon's journey to the planet's electromagnetic output. These emissions, now known as Io-controlled decametric radio emissions, turned Jupiter and its moon into a cosmic lighthouse. As Io travels along its orbit, it effectively tilts Jupiter's magnetic field, creating a current of charged particles that flows between the moon and the planet's polar regions. When conditions are just right, this current becomes unstable, triggering a cascading release of energy that accelerates electrons to nearly the speed of light, resulting in a brilliant burst of radio static that we can detect across the great gulf of space. Yet the precise and complex nature of this relationship is where the true mystery lies. You might think that if we know Io's position, we could perfectly predict when these radio bursts will occur. But the reality is far more frustrating and fascinating. The connection is not a simple on-off switch. The intensity and timing of the emissions are influenced by a delicate interplay of at least three key factors: Io's exact position in its slightly elliptical orbit, the ever-changing level of volcanic activity on Io itself, and the constantly shifting density of the plasma torus that the Moon creates. It's as if we are trying to predict the exact moment a specific wave will crash on a shore by knowing the position of the Moon, the wind speed, and the underwater topography all at once. Our current models can only tell us when the conditions are favorable for a burst, not when one will definitely happen. The difficulty in making accurate predictions is a clear signal that our understanding of the plasma environment around Jupiter is incomplete. The Io plasma torus is not a smooth, uniform donut of gas. It is a turbulent and dynamic structure with ripples, clumps, and waves moving through it. Small variations in the density of this torus can dramatically alter how the electrical current flows between Io and Jupiter, either enabling a powerful radio burst or suppressing it entirely. Furthermore, Io's volcanic output is not constant. A major eruption could inject a fresh cloud of material into the torus, changing its properties for weeks or months and altering the entire system's behavior in ways we are still learning to anticipate. This means the link is not just a mechanical one based on orbits. It is a living, breathing system where geology on a moon directly influences the plasma physics around a planet. Unraveling this mystery is crucial because it represents a fundamental process that likely occurs throughout the universe, wherever a magnetic planet interacts with a volcanic moon or a source of plasma. By deciphering the precise rules governing the Io-Jupiter system, we gain a master key for understanding similar interactions in distant star systems. Each unpredictable burst of radiostatic is a message, a complex cipher containing information about the strength of magnetic fields, the behavior of high-energy particles, and the intimate gravitational dance between worlds. Cracking this code requires continuous monitoring and increasingly sophisticated computer models, a long-term effort to listen carefully to the complex and ever-changing song of the giant. We have explored the violent weather, the hidden interior, and the profound influence Jupiter wields over its moons and magnetic environment. But to truly grasp the scale of this world, we must confront the most fundamental and awe-inspiring mystery of all: its sheer, almost incomprehensible size and mass. Jupiter is not merely a large planet, it is the planetary titan of our solar system, a colossus whose mass is greater than all the other planets combined, multiplied by 2. To stand on its cloud tops, if such a thing were possible, would be to experience a gravity so powerful it would crush a human being instantly. This immense bulk is the source of its every power, from the churning dynamo of its magnetic field to the storms that rage for centuries. Yet, this very greatness presents a central puzzle that reaches back to the dawn of our solar system. Why did Jupiter stop growing? What force or circumstance placed a cap on the expansion of this cosmic giant? The story begins over 4.5 billion years ago, within the swirling, dusty disk of gas and rock that encircled our infant sun. In this primordial nursery, Jupiter was the first planet to form, and it had a monumental head start. The leading theory, known as core accretion, suggests it began with a solid seed of rock and ice, because it formed beyond the frost line, the distance from the sun where water and other volatile compounds could exist as ice. This seed had an abundance of building material. It grew rapidly, and once it reached a critical mass of about 10 to 15 times the mass of Earth, a breathtaking transformation occurred. Its gravitational pull became strong enough to start directly capturing the vast reserves of hydrogen and helium gas from the surrounding protoplanetary disk. This was the moment it became a true gas giant, embarking on a period of runaway growth that should, in theory, have continued almost without limit, but it did stop. Jupiter, for all its immensity, is not a star. It never accumulated enough mass to ignite the fusion fires in its core that would have turned it into a brown dwarf or even a small star. So, what applied the brakes? One compelling explanation is that it simply ran out of food. The protoplanetary disk was not infinite, it contained a finite amount of material. Jupiter's own formation may have been so efficient that it effectively consumed all the available gas within its gravitational reach, starving itself into its current state. It's a plausible idea, but many scientists believe the process was more active and dynamic than a simple emptying of the pantry. This leads to a more elegant and widely accepted theory involving the planet's own gravitational influence on the disk itself. As young Jupiter plowed through the gas and dust, its gravity began to carve a path, clearing a wide, empty gap in the disk around its orbit. You can picture this like a massive snowplow creating a clear lane on a snowy road. Once this gap was established, the flow of fresh material from the outer regions of the disk toward the growing planet was severely restricted. The very mechanism of its growth, its gravity, eventually became the barrier that halted it. The planet created a moat around itself, cutting off the supply lines of gas that were fueling its expansion. This self-limiting process likely set the ultimate size for not only Jupiter but for Saturn as well, explaining why we have two large gas giants instead of one single, star-sized behemoth dominating our system. This colossal mass, once achieved, did not make Jupiter a passive spectator in the solar system. Instead, it cast the planet in a role of profound importance, that of a gravitational guardian. Jupiter's immense gravity acts as a cosmic vacuum cleaner, or perhaps more accurately, a gravitational shield. The solar system is filled with countless asteroids and comets, remnants from its formation that travel on unstable, often dangerous orbits. When one of these objects ventures too close to Jupiter, it faces a dramatic fate. It can be flung outward, ejected from the solar system entirely into the icy depths of interstellar space. Alternatively, it can be pulled inward on a collision course with the Sun, or captured by Jupiter's gravity to become part of its entourage of moons or to crash into the planet itself, as witnessed with the Shoemaker-Levy 9 impacts in 1994. This activity has had a direct and beneficial impact on Earth. By clearing a significant portion of this celestial debris, Jupiter has likely reduced the frequency of catastrophic asteroid and comet impacts on our planet over geological time. This gravitational sweeping may have provided a more stable environment for life to emerge and evolve, making Jupiter an unwitting protector of the inner solar system. However, this role is a double-edged sword. Some dynamical models suggest that Jupiter's gravity can also perturb objects from stable orbits in the asteroid belt, occasionally sending them on new trajectories that cross Earth's path. The nature of Jupiter's influence, whether it is primarily a shield or a threat, is a nuanced question that depends on the specific orbits of the objects involved. But its overwhelming gravitational presence is undeniably the dominant force shaping the population of small bodies in our cosmic neighborhood. The mystery of Jupiter's final mass, therefore, connects directly to the architecture of our entire planetary system and the conditions that made our own world possible. If Jupiter had continued to grow, becoming significantly more massive, its gravitational influence would have been even more extreme. It could have prevented the formation of the other planets entirely or destabilized their orbits, creating a chaotic and vastly different solar system. The fact that it stopped where it did was a critical event, a balancing act between the available material and the physical processes within the protoplanetary disk. This raises a fascinating prospect as we look outward to the thousands of exoplanets discovered around other stars. We see many hot Jupiters, gas giants orbiting extremely close to their suns, and super-Jupiters that are far more massive than our own. Understanding the precise brakes applied to Jupiter's growth helps us create models for how planetary systems form and evolve across the galaxy, revealing that our giant's specific size is not just a random fact, but a key piece of evidence in the ongoing investigation into the diversity of worlds in the cosmos. Yet, for all our focus on the violent forces and ancient history of this giant world, perhaps the most captivating question of all remains: could Jupiter be alive? Not in the geological sense, but in the biological one. Is it possible that within those churning, irradiated, and tempestuous cloud decks, a form of life, utterly alien to anything we know, has taken hold? It is a concept that stretches the imagination to its absolute limit, a speculative leap that transforms Jupiter from a mere physical marvel into a potential biological frontier. The surface, or rather the point where the pressure becomes crushing, is certainly a hellish environment unfit for any life we can conceive. But as we rise higher into the atmosphere, the conditions, while still extreme, become surprisingly familiar in certain key ways. This fascinating line of thinking was championed by none other than the visionary astronomer Carl Sagan, along with his colleague E. Salpeter. They looked past the planet's obvious hostility and asked a profound question. If life on Earth can flourish in a stunning variety of niches, from scalding hydrothermal vents to frozen Arctic tundra, why could it not adapt to the vast, three-dimensional ocean of a gas giant's atmosphere? On Earth, we have simple, floating organisms like plankton that drift on ocean currents. Sagan and Salpeter imagined a Jovian equivalent, but on a scale befitting the king of planets. They envisioned hypothetical life forms they called floaters. These would not be microscopic, but gigantic, balloon-like creatures, perhaps kilometers across, that would essentially be living blimps. Their immense size would be a necessity, a way to navigate the powerful currents and stabilize their position within a specific, hospitable layer of the atmosphere. The survival strategy for such a creature would be as elegant as it is strange. It would need to maintain a delicate balance with its environment. The floater's body would likely be filled with a gas lighter than the surrounding hydrogen-rich atmosphere, perhaps hydrogen or helium itself, harvested directly from the air. This would provide buoyancy, allowing it to float effortlessly, much like a hot air balloon floats in our own sky. But Jupiter's atmosphere is not static. It is a violent arena of rising and sinking columns of gas. To avoid being dragged down into the crushing, hot depths or pushed up into the frigid, irradiated upper layers, the floater would need a sophisticated way to navigate. Sagan and Salpeter suggested it might do this by actively managing its internal gas composition or temperature, altering its buoyancy to catch specific convection currents, riding the planetary weather system like a soaring bird rides thermal updrafts on Earth. It would spend its life in a perpetual, graceful dance with the storms, seeking out the narrow band where temperature, pressure, and chemistry are just right. And what would it eat? This is where the concept moves from mere speculation to a tantalizing possibility grounded in chemistry. We know that Jupiter's atmosphere is rich in the basic building blocks of life as we know it: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Sunlight and lightning provide ample energy to drive the formation of complex organic molecules, the precursors to life. The floater could be a filter feeder of sorts, using vast membranous surfaces to absorb these prebiotic compounds directly from the air. Or it could exist as the top of a simple food chain. Sagan and Salpeter also imagined smaller, rapidly reproducing organisms they called sinkers. These would be simple, perhaps microbial life forms that condense out in the upper atmosphere and then slowly fall, multiplying as they descend. The giant floaters would then consume these sinkers, harvesting the organic material that rains down from above in a continuous celestial harvest. Of course, this entire idea remains firmly in the realm of scientific speculation. We have no evidence whatsoever that such life exists on Jupiter. The challenges are immense: the intense radiation, the violent turbulence, the scarcity of liquid water, a solvent we consider essential for life. Any Jovian biology would have to be based on a completely different biochemistry, perhaps using liquid ammonia or sulfuric acid as a solvent instead of water. Yet, the value of this thought experiment is incalculable. It forces us to expand our definition of a habitable environment. We traditionally look for Earth-like planets orbiting in the Goldilocks zone of their stars, but Jupiter demonstrates that a habitat doesn't need a surface at all. A stable, layered atmosphere with the right mix of chemicals and an energy source could, in theory, be a home. This makes Jupiter the ultimate laboratory for thinking about life on the thousands of gas giant exoplanets we have discovered. If life can find a way in the clouds of Jupiter, then the potential for biology in the universe explodes exponentially. We are no longer limited to rocky worlds. The countless gas giants orbiting other stars become potential abodes for floating, soaring ecosystems. The mystery of life on Jupiter, therefore, is not just about one planet. It is a paradigm shift, a challenge to our geocentric view of habitability. It asks us to look at the swirling face of the giant and wonder if within its tempests there might not just be chaos, but an entire, unseen and breathtaking form of existence. We have journeyed through storms larger than worlds and gazed upon auroras that dwarf our entire planet, but now we must confront an invisible prison of pure energy that surrounds Jupiter, a structure so hazardous it has shaped our very approach to exploring the giant. Encircling the planet far beyond its faint, dusty rings are the most intense and formidable radiation belts in our solar system. These are Jupiter's version of Earth's Van Allen belts, but elevated to a truly monstrous scale. Imagine a donut-shaped zone of space millions of miles across, filled not with harmless dust, but with a frenzied soup of electrons and protons accelerated to nearly the speed of light. This radiation is so powerful that an unshielded spacecraft would have its electronics fried in a matter of hours, and any hypothetical astronaut would receive a lethal dose in minutes. The sheer ferocity of this environment is a direct consequence of Jupiter's incredible magnetic field, which acts as a giant natural particle accelerator, trapping and whipping these charged particles into a sustained frenzy. The complexity of these belts, however, goes far beyond a simple shell of radiation. One of the most intriguing mysteries discovered by spacecraft is the presence of a radiation slot, a region within the belts where the intensity of particles suddenly drops. On Earth, a similar slot in our own Van Allen belts is cleared out by interactions with our planet's upper atmosphere and by very low-frequency radio waves. But Jupiter has no solid surface to provide an atmospheric buffer, so what could possibly be carving out a safe passage within this maelstrom? The answer, once again, lies with Jupiter's tiny, enigmatic moons. The moons Amalthea and Thebe, which orbit within the heart of the radiation belts, act as natural vacuum cleaners. As they travel along their paths, they literally sweep up the high-energy particles in their immediate vicinity. Any particle whose orbit brings it too close to one of these moons will be absorbed by the moon's surface, effectively clearing a gap in the radiation field. This creates a discernible dip in the radiation levels, a celestial toll booth where the moons have levied a tax on the particle population. Yet, the moons don't just passively clear space. Their interaction with the radiation environment is a dynamic and violent dance. The process works both ways. While the moons absorb some particles, the relentless bombardment of radiation on their surfaces has a dramatic effect on the moons themselves. This constant particle blasting kicks up or sputters atoms from the moon's surfaces, injecting new material into the surrounding space. This ejected material becomes ionized, adding to the complex plasma environment that Jupiter's magnetic field must then contend with. It is a continuous feedback loop. The moons shape the radiation belts by absorbing particles, and the radiation belts, in turn, erode the moons and replenish the plasma that fuels the entire system. This intricate relationship turns the region around Amalthea and Thebe into a natural laboratory, allowing scientists to study how solid bodies and intense radiation fields coexist and evolve over time. Understanding the precise structure of these belts is not merely an academic exercise. It is a matter of survival for our robotic explorers. Every mission to the Jovian system, from Galileo to Juno and the upcoming Europa Clipper, must be meticulously designed to withstand this onslaught. Spacecraft engineers use detailed maps of the radiation belts to plot trajectories that minimize exposure, often using the Moon's gravitational pulls to swing the spacecraft into orbits that avoid the most intense zones. The electronics within these probes are housed in a radiation-shielded vault, a titanium-lined safe that protects their delicate brains from the constant particle hail. Each successful mission provides more data, which in turn refines our models, creating a virtuous cycle of discovery and engineering that pushes the boundaries of what is possible in deep space exploration. The ultimate mystery woven through these invisible rings is the fundamental physics of particle acceleration itself. How does Jupiter's magnetic field take relatively tame charged particles and energize them to such extreme velocities? The process is thought to be a combination of several mechanisms. One is akin to a cosmic version of a surfer catching a wave. Particles can gain energy by interacting with plasma waves that ripple through Jupiter's magnetosphere, riding these waves to higher and higher speeds. Another involves the planet's rapid rotation. The spinning magnetic field creates immense electric fields that can violently accelerate particles along the field lines. Jupiter serves as a nearby example of processes that occur around pulsars, magnetars, and distant astrophysical jets, but on a scale we can actually visit and measure. By deciphering the secrets of its radiation belts, we are peering into the fundamental engines that shape not just our solar system, but the most energetic corners of the universe. And so we reach the end of our extraordinary expedition, having journeyed from the planet's hidden, fuzzy heart to the dazzling light shows that crown its poles. We have navigated the endless churn of its striped atmosphere, witnessed the geometric perfection of its polar cyclones, and grappled with the unseen forces of its titanic magnetic field. We have seen how this single world acts as a gravitational architect, a cosmic shield, and a relentless puzzle, constantly challenging our assumptions about how planets form and behave. Each of these 25 mysteries, from the shrinking great red spot to the bizarre ammonia plumes and the scorching hot shadows, is a thread in the grand tapestry of Jupiter, a tapestry that is far from complete. The incredible truth that missions like Galileo and Juno have revealed is not that we have solved Jupiter, but that we have merely begun to appreciate the depth of its secrets. Every answered question has unveiled two more, proving that this giant is a master of deception and complexity. It has shown us that a world without a solid surface can possess more intricate weather than our own, that a planetary core can be a diffuse cloud rather than a solid ball, and that the interactions between a planet and its moons can create phenomena of breathtaking power and beauty. Jupiter stands as a humbling reminder that for all our technological prowess, the universe retains a capacity for wonder that exceeds our imagination. Yet the story of Jupiter is still being written, and the next chapter is already underway. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE, is now en route with a mission focused squarely on the potential habitable environments of Ganymede, Callisto, and Europa. But to understand those moons, it must first understand their master. JUICE will build upon Juno's legacy, using its powerful suite of instruments to peer even deeper into Jupiter's atmosphere, to map its magnetic field in unprecedented detail, and to study the complex interplay between the planet and its lunar family. It represents a new era of exploration, one that views the Jovian system as a single, interconnected entity, where the planet's immense influence shapes the destiny of every world that orbits it. The journey of discovery is perpetual, and each new mission brings us closer to unraveling the enigmas of this gas giant. But the exploration does not belong to scientists alone. It is a shared human endeavor, fueled by the curiosity of everyone who looks up at the night sky and wonders. So now we turn the question over to you. Which of Jupiter's profound mysteries captures your imagination the most? Is it the possibility of life floating in its upper clouds, the ancient migration that may have shaped our solar system, or the relentless, centuries-old fury of the Great Red Spot? Let us know in the comments below, and if you've enjoyed this deep dive into the King of Planets, be sure to subscribe. Our journey through the cosmos is far from over, and there are countless more secrets waiting to